Now, how can we graph polar equations without converting them to Cartesian form? So usually what we do is the usual one where we set up a table of values. But it would also be helpful if we check the symmetry of those graphs so that we don't need to create a lot of points or make a table for a lot of points. Now, we have to check the symmetry of a polar graph in three forms. If it's symmetric with respect to the polar axis, with respect to the pi over 2 axis, and with respect to the pole. If it is symmetric to the polar axis, then the equation remains the same if we replace r theta with r negative theta or negative r and pi minus theta. Now, if it's already equivalent on this, you don't need to check this anymore. However, if for example there's no equivalent equation here, then you have to check here first. If in the event that there is no, there's no equivalent equation on both, then it's a bit, then that's the one thing that we say that it might not be symmetric. But remember, an equation may fail this and still have a graph symmetric. But at least when we try to graph it on our end, if it fails these two, then we don't expect, even though it is still possible, we don't expect that they are symmetric. So again, it's symmetric to a polar axis if we replace r theta with this. If this alone, it follows that it's symmetric. If it doesn't follow, then we try to check here. If it follows here, then it is symmetric with respect to the polar axis. If it doesn't work for both, then we try to assume that it's not. We do the same, but for the pi over 2 axis, we replace r and theta. Instead of replacing r, we just replace r with theta with pi minus theta. Or if we do replace r, we replace it with negative r and negative theta. So again, just like in the polar axis, we check this first. If it works here already, then you don't need to check on the other one. But if it doesn't work here, then you check here first. And then you check there next. That goes the same here with respect to the pole. You check here first. If it doesn't work here, then you check on the other one. May I repeat that? The first thing that you check for pi over 2 axis is this one. This one first. This is the first one. Then you check this is the second one. The one without the binomial with pi is the one that you check first. So for pole, this is the first one. For polar axis, this is the first one. But then again, it might not work on the two, but still symmetry. So before we go to testosymmetry, let's now try to first analyze what are some of the basic graphs, polar graphs, that we're going to encounter. One of the most basic graphs, or the most usual graphs that we see in the polar coordinates, would be Limaçons. So Limaçons are these curves here that would look like a circle, but it's not actually a circle. So the form of the equations for Limaçons is r is equal to a plus or minus b cosine theta, or r is equal to a plus or minus b sine theta. If it's cosine theta, then the Limaçon is symmetric with respect to the polar axis. If it's positive, then it points to if it's plus in between a and b cosine theta, it points to the right. If it's negative, it points to the left. If it's sine theta, then the Limaçon is most probably symmetric with the pi over 2 axis. If it's plus, it points upward. If it's minus, it points downward. So that's also additional tips to get just in case we need to test for symmetry. We can expect that if we see this equation, this is symmetric with respect to the polar axis. If we see this equation, it's symmetric with respect to the pi over 2 axis. Now, there are 4 types of Limaçons. If the ratio between A and B would be negative, would be less than 1, not necessarily negative, but less than 1, say 1/2 or 1/4, then the limaçon has an inner loop. This one here. If A and B would be equal because they make a ratio of 1, then the limaçon is a cardioid, so-called because it looks like a heart. So cardioid. If A and B would be in between 1 and 2, 1.5 or 3 halves, and so on, then the limaçon is dimpled. The point of the cardioid is not on the pole. It's somewhere here on the polar axis. And if A over B is greater than or equal to 2, it's a convex limaçon, and the dimple somehow flattens on this side. So those are the 4 types of limaçons. So let's try to see and practice and also apply the symmetry test when we graph samples of our limaçons. So let's try to graph number 1. R is equal to 1 plus cosine theta. Now, before we do the symmetry test, based from this, we know that it's a limaçon because of its form, A plus B cosine theta. And since it's cosine theta, we expect that it is symmetric with respect to the polar axis because it's cosine theta and it's a limaçon. As we can also see, A is equal to 1 and B is equal to 1, which obviously when you make a ratio, it's equal to 1. Therefore, we expect that this is a graph of a cardioid. So, now that we have set our expectations, let's try to see if it's really symmetric with respect to the polar axis. So, let's now do our symmetry tests. So, the first thing to do, if it's symmetric with respect to the polar axis. So, for the polar axis, let's first check. We replace r theta with r negative theta. Put this here. R negative theta. There you go. So, r plus 1 is equal rather to 1 plus cosine theta. We just change it to r is equal to 1 plus cosine of negative theta. Then using our knowledge of trigonometric identities, see what we will come up with. If you remember, in odd and even identities, we say that cosine of negative theta, if we write it below, the cosine of negative theta is just equal to cosine theta. So therefore, by this identity, we then say that r is equal to 1 plus cosine theta, which is exactly the same as the original. This is what we mean when we say that even though we replace theta with negative theta, it goes back to the original form. Therefore, it is really true that it is symmetric with respect to the polar axis. We write the conclusion as such. Therefore, symmetric with respect to the polar axis. Now, let's check if it is symmetric to the pi over 2 axis. Although if you're going to check the previous slide, a cardioid doesn't seem to be symmetric with respect to pi over 2 axis. So, let's check that. For pi over 2 axis, the first thing that we need to do is check if it is symmetric. If we replace with negative r, negative theta, it will come the same. Now, take note that we have already replaced this with negative theta. That's 1 plus cosine of negative theta. And taking note of that makes the computation easier. Then we just replace r with negative r. So this becomes negative r. We already know that this is the same as 1 plus cosine theta. So since we are aiming for this to be positive, so we multiply both sides of the equation by negative 1. So remove that negative. This becomes r is equal to negative 1 minus cosine theta. which is not the same, which is not the same as that one. Therefore, at this point, it's not symmetric to the pi over 2 axis. But, remember, we need to check if it's also not symmetric if we replace r theta with r pi minus theta. This is where it gets long. R is R, so we don't have much to worry about, but it becomes 1 plus cosine of pi minus theta. But we can simplify this using our difference identity. So this becomes R is equal to 1 plus cosine pi cosine theta plus sine pi sine theta. So simplifying this, we're going to get R is equal to 1. Cosine pi is negative 1. So that's negative 1 times cosine theta. That's minus cosine theta. And sine pi is 0. So 0 times sine theta is 0. So we don't need to write that. So we get R is equal to 1 minus cosine theta, which is not the same as the original one. I need to write the original one in this image. It's not the same as the original one, and we have already checked that it doesn't work here, it doesn't work here. Therefore, we can conclude that it is not symmetric. Not symmetric with respect to the pi over 2 axis. Now, the last thing to check if it's symmetric with respect to the pole. So if it's symmetric with respect to the pole, then we have to check first with negative r theta. So if it's negative r theta, we all need to do if it's negative r, then 1 plus cosine theta. And we know that if we do this, it comes up like this. R is equal to negative 1 minus cosine theta. So it doesn't work here. If we replace this with r pi plus theta, then we would have to compute. R remains the same, so it becomes 1 plus cosine of pi plus theta. So therefore, we want to have 1 plus, using our sum identity, cosine pi cosine theta minus sine pi sine theta. We know from here that sine pi is 0, so we cancel that. And cosine pi is negative 1. Since this is plus, that becomes 1 minus cosine theta. And r is equal to 1 minus cosine theta is not our original. So therefore, it is also not symmetric with respect to the pole. So it's only symmetric with respect to the polar axis. So now that we got that clear, we now can make a smaller table of values. Now, how do we do that? There you go. So, since this is cosine theta and we're graphing, then we can use the key points when we graph cosine theta. If you recall, with a period of 0 to 2 pi, we usually divide 2 pi to 4, and we get pi over 2. From there, the key points that we would have would be 0, or the interval rather, interval that we use is 0, pi over 2, pi, 3 pi over 2, 2 pi. So we use these values and substitute it here to get the value of r that we have. So this is theta and this is r. So that's the short table of values that we get. 0, pi over 2, pi, 3 pi over 2, 2 pi. Then let's also graph our polar axis and pi over 2 axis. Pi, there you go, pi over 2 axis. So cosine 0 is 1, so plus 1, that would be 2. Cosine pi over 2 is 0, so that's 1 plus 0, that makes it 1. Cosine pi is negative 1. So if this is negative 1, 1 plus negative 1 is 0. Cosine 3 pi over 2 is 0, so that's 0 plus what? 1. And cosine 2 pi is 1, so 1 plus 1, that gives it 2. So therefore, if we plot these points, 2, 0, radius is 2, but theta is 0, that would be here. That is the point 2, 0. Radius of 1, but theta is pi over 2, it's here. Radius of 0, so it's here. Even though it's pi, so that would be at the pole. 1, 3 pi over 2, this is 3 pi over 2, this is 1. 2 and 2 pi is this. Sorry, I moved, this is what is here. So this is the 4 points that we have. Since it's symmetric in the pi over 2 axis, it should look exactly the same here above and here below. And since we know it's a cardioid, it should look like somewhere like a heart. So when we try to sketch the graph, please forgive me not good at drawing, especially if it's online. It should look something like this. Although it looks a bit ugly. It should be a bit rounder here. Let's do that again. Oops. We can make it like that. So there, that's a very rough sketch of what a cardioid can look like. Although you can search the internet for what it really looks like, because it looks really a bit, oops, here, it looks a bit rounder here. So that's what it can look like. It's just a bit difficult to graph here, actually. So, it's a bit long of a process, but it's a matter of practice. Now, try to pause the video and see if you can sketch the graph of number 2. R is equal to 2 minus 4 sine theta. Alright, so assuming that we actually paused the video, let's analyze and let's see how we can sketch the graph of R is equal to 2 minus 4 sine theta. So based from this is a Limaçon. And specifically, since it's sine theta, the Limaçon is expected to be symmetric with respect to the pi over 2 axis. And since A is equal to 2, B is equal to 4, the ratio is 2 over 4, which is equal to 1/2, which is in between 1 and 2. Sorry, not in between 1 and 2, but less than 1. So therefore, the graph is a Limaçon with an inner loop. There we go. Now, I'm not going to show anymore the long computation for our symmetric test, but for the polar axis, maybe to make it shorter, if you're going to double check, it really doesn't work. It's not symmetric. It's not symmetric. With the polar axis, and pole. It's only symmetric to the pi over 2 axis, and I leave it to you to make sure that the computation is aligned with these conclusions. So if we're going to graph, again, our theta, we'll use the same key points for 0 to 2 pi. That's 0, pi over 2, pi, 3 pi over 2, and 2 pi. There you go. So for R, so there. So we have sine 0 is 0, times 4 is 0, 2 minus 0 is 2. Sine pi over 2 is what? 1 times 4 is 4. So 2 minus 4 is negative 2. Sine pi is 0. So 0 times 4 is 0. 2 minus 0 is 2. Sine 3 pi over 2 is negative 1. Negative 1 times 4 is negative 4. 2 minus negative 4, that is 6. And 2 pi, sine 2 pi is 0. 0 times 4 is 0. 2 minus 0 is 2. So if we're going to plot these points, r is 2 but theta is 0. Here you go, r is 2, theta is 0. Negative 2 pi over 2. It's pi over 2 here, but negative 2 here. 2 and then pi. 2 pi. 6 and then 3 pi over 2. 1. So that's 1, 2, 3, 4, 5. Oops. 1, 2, 3, 4, 5, 6. This is 6, 3 pi over 2. And 2 pi is this one. So based from this, it's a limaçon with an inner loop. It looks like this. It crosses it crosses the pole. So it can look at its symmetric with respect to the pi over 2 axis. So it somehow looks like this. I hope I can draw it correctly. It has an inner loop. So like that. Oops. There you go. Wait, look, I do it. There you go. It's not bad. I know I'm not good at drawing forward. If I can not. So it looks like actually card. Somehow looks like these are the so this is the actual of the there you go. And then it doesn't look any better, but that's what a limaçon with an inner loop. This is what the sketch of r is equal to 2 minus 4 sine theta looks like. Now let's proceed to another graph which is a rose, or which are roses. So if the graph or the equation looks like r is equal to a sine n theta, or r is equal to a cosine n theta, then the graph must be a rose. A is the size or the radius of the rose, and n is the number of petals. If n is even, then we have to multiply it to 2 to get the number of petals for that. So a cosine 2 theta, 2 times 2, that's 4. You have a 4 leaf or a 4 petaled rose. Similarly, if n is equal to 4, 4 times 2, 8. You have an 8 leaf or 8 petaled rose. But if n is odd, it remains the same. If n is equal to 3, you have a 3 leaf rose. If n is equal to 5, you have a 5 leaf rose. And n will have an effect when we compute the intervals on what theta we're going to use. Now, let's try to sketch a graph of a rose. So let's work with number 1. We have number 1 is equal to r is equal to 2 sine 2 theta. So that you'll be able to review the different tests for symmetry for polar graphs, pause the video and try to do the symmetry tests for our equation r is equal to 3 sine 2 theta. So assuming you have done so, let's show the computations for each symmetry test. So first, let's have for the polar axis. For the polar axis, we'll have r, then negative theta first. So substituting it there, r will be equal to 3 sine, that's 2 times negative theta. So this becomes 3 sine negative 2 theta. Due to odd and even functions of sine negative theta is equal to negative sine theta, this will then become r is equal to negative 3 sine 2 theta. Not the same as the original, so it doesn't work here. Let's try if it would work with negative r and pi minus theta. Okay, let's just bring that up. There you go. So from there, we'll have negative r is equal to 3 sine 2 times pi minus theta. So we have to distribute the 2. So negative r would be equal to 3 sine 2 pi minus 2 theta. So this we have to expand using difference identity. So we'll have negative r is equal to 3 multiplied 2 sine 2 theta sine 2 pi cosine 2 theta minus cosine 2 pi sine 2 theta. Sine 2 pi is equal to 0, so this gets cancelled. So we're going to negative r is equal to 3 times, since cosine 2 pi is 1, it becomes negative sine 2 theta. Therefore, we'll have negative 3 is equal to negative 3 sine 2 theta. Both negative, so we can divide both sides by negative 1 or multiply both sides by negative 1. R will be equal to 3 sine 2 theta. And this works. This works. Therefore, this is symmetric with respect to the polar axis. Now let's check if this is symmetric with respect to pi over 2 axis. Pi over 2 axis. So first, to check if it's symmetric with respect to the pi over 2 axis, have negative r, negative theta. We'll enter the result of negative theta here. Let's just write it down. It's 3 sine of 2 times negative theta. This will ultimately lead us to r is equal to negative 3 sine 2 theta. And since they're both negative here, we can conclude that r is equal to 3 sine 2 theta. Therefore, it is symmetric with respect to the pi over 2 axis. Symmetric with respect to the pi over 2 axis. Now, let's check if it's symmetric with respect to the pole. First, let's check if it's negative r theta, which is quite easy. That's negative r is equal to 3 sine 2 theta. R would then be equal to negative 3 sine 2 theta. Not the same as the original. What about if we change it to r and then pi plus theta? So r will be equal to 3 sine of 2 times pi plus theta. Therefore, this will be equal to 3 sine of 2 pi plus 2 theta. We have to expand this using a sum identity. It becomes 3 multiplied by sine 2 pi cosine 2 theta plus cosine 2 pi sine 2 theta. So this becomes sine 2 pi is 0, this gets cancelled, and cosine 2 pi is 1. So therefore, I'm going to have r is equal to 3 sine 2 theta, which is the same. Therefore, it is also symmetric with respect to the pole. So it's symmetric to all three. Now, when we go up and find our table of values, the one thing that you'll notice is this. 2 times 2, that's n, that will be 4 petals. What is the effect of 2 now when we create that table? So, if you remember, when we get the interval and the period when we were sketching the graph of trigonometric functions, we equate this to 0 and then to 2 pi to get the endpoints, the starting point and then the endpoint. So if we do so, theta is equal to 0 here. If we divide this, theta will be equal to pi. This is telling us that our interval now will be 0 to pi. 0 to pi. If we divide pi by 4, therefore this is the interval that our theta would first be 0, pi over 4, then continuously add pi over 4. So pi over 4 plus pi over 4, pi over 2, then 3 pi over 4, then pi. So times 2 of that, it becomes 0, pi over 2, pi, 3 pi over 2, 2 pi, which is what we easily compute to get r. So that becomes 3 times sine 0 is 0. So 3 times sine pi over 2, that's 3, because sine pi over 2 is 1. Sine pi is sine pi is 0 times 3 is 0. Sine 3 pi over 2 is negative 1 times 3, that's negative 3. Sine 2 pi is 0 times 3 is 0. But what we graph is this and this. So therefore, 0, 0, oops, let's first place our polar axis, oops, polar axis, and our pi, oops, missed a bit, pi over 2 axis. So 0, 0, 0, 0, 0, 0 is here. Pi over 4, 3, then pi over 4. So 1, 2, 3, pi over 4 is here. 0, pi over 2, so it's back here. Negative 3, 3 pi over 4. 3 pi over 4 is here, but since it's negative, we go down here. 1, 2, 3. Here. Then 0, 2 pi. If we're going to take a look at the first graph, it looks like, oops, it's a bit hard to make it, oops, it's hard to make it a bit round. It has to be somehow looking like, wait, let's fix that. Yep, sorry, that will do. Now, this is what we got from these points. But we know that since this is 2, that's 2 times 2, we have 4 petals. Since we know that it's symmetric with respect to the polar axis, this is the symmetric with respect to the polar axis. Since it's also symmetric with pi over 2 axis, this has to have the same as on the left side of pi over 2. At the same time, since it's symmetric with respect to the pole, quadrants 1 and 3 should have the same, 2 and 4 should have the same. Therefore, because of that symmetry, this carries over to 3 pi over 4, this carries over to 5 pi over 4. 1, 2, 3, here. So therefore, we should also have a petal here, and a petal here. So that's the rough sketch of r is equal to 3 sine 2 theta. Let's try to sketch this graph. I'm not going to show the detailed solution anymore for the test of symmetry, but this graph, first, it's a rose that has 3 petals. Rose with 3 petals, oops. 3 petals, and this 2 here is the radius of the rose. From there, for our symmetry test, we can say that it's symmetric with respect to the polar axis and just the polar axis. If you please check, and I'll leave the computation to you, that it will show it's not symmetric with the pi over 2 axis and the pole. Now, if we are to sketch the graph here, since this is 3 theta, so 3 theta would be equal to 0 and 3 theta would be equal to 2 pi, dividing, so our interval would be from 0 to 2 pi over 3. And if 2 pi over 3 is divided by 4, I'm going to get pi over 6. So therefore, my theta would be from 0. Theta would be from 0, pi over 6, pi over 3, pi over 2, 2 pi over 3. So for 3 theta, this will become 3 times 0, that's 0. 3 times pi over 6, pi over 2, pi, 3 pi over 2, and 2 pi. So for r, the value of r, this becomes 2, 0, negative 2, 0, and 2. If we graph that, 2, 0 is here, 0 pi over 2, 0 pi over 2, negative 2 pi, this is 2 pi but negative 2 is here, 0 pi over 2 and 2 pi here. Now, since we only have 3 petals, this is the only thing that we got. 2, 0, 0, negative 2, 0, 3 pi over 2, and this is the only thing that we got. How can we now sure what the others will look like? Now, a 3 petal rose, if you're going to check here, looks like this. So let's use symmetry to get the values here. Oops, sorry, I think I made a mistake. 0, sorry, let's graph that again. So let's graph it again. So we have here 0, 2, pi over 6, 0, negative 2 pi over 3, if I made a mistake a while ago on our angle. So pi over 3 is here, but since it's negative 2, 1, 2, it's here. There you go. 0 pi over 2, see? Then 2 pi over 3. 2 pi over 3 is here, is 2, 1, 2. So here, this is what it looks like. I apologize. Again, you start from this theta. I started here. That's wrong. So you start from this theta. As you can see, we have 3 points here. So if we're going to sketch the graph, oops, it will look something like this. Oops. Like this and then like that. So now, although it's a bit weird, but that's what this rough sketch of r is equal to 3, 2 cosine 3 theta would be. So we have one last graph to show, but let's place it on our next video.